Okay, so in this problem we have our spring with a heavy mass M attached. The spring has mass M, it has length L and the spring constant K. We're considering a segment which is a length X from the end and has thickness dx. And in part A, we're asked what's the kinetic energy of the spring. So to work this out, what we need to do is add together the kinetic energy of each of these little dx sections. So the velocity of each of those sections, Vx, is equal to x over L v, where v is the velocity of this block on the end. And we know that the mass of each of those sections, dm, is just the mass per unit length, which is the m on L, times dx, the length of that section. So to get the kinetic energy, we know kinetic energy is a half mv squared, so we just need to sum together the mv squared from each of these little dx's. So to do that, we integrate all along the spring, so from 0 to L. The mass of each of those sections is given by m over L dx, and the velocity of each of those sections is x over L v all squared. Okay, so this is a half. Now we can pull the m on L out because that's not a variable. This L, 1 on L squared, is not a variable, and v squared is also not a variable. And so what we're left with integrating is x squared dx from 0 to L. So integrating that, we have a half mv squared over L cubed, and then this, when we integrate it, we get x cubed on 3 from L to 0, and so that's going to be a half mv squared on L cubed. Substituting in these numbers, we get L cubed on 3. The 0 disappears, and so those cancel out, and we have a sixth mv squared is the total kinetic energy of the spring. So that's the answer to part A. For part B, we're asked to find the period for oscillations. What we'll need to do is work out omega, and then we know omega is equal to 2 pi on t. And so from omega we can work out the period. Okay, so the total kinetic energy for the spring plus the block is equal to 1/6 mv squared plus 1/2 capital M, that's the mass of the block, v squared. So this is equal to a half 1/3 little m plus big M v squared. So what we've got here is an effective mass. This is the effective mass, m effective, including the mass of the spring. Generally in this question we assume that it's a very light spring and we don't need to consider the kinetic energy of the spring, but in this case we do. So what this is telling us is that we can replace in our normal equations the mass with the effective mass, which is given by this. And so omega is equal root k over the effective mass, which is the square root of k over 1/3 little m plus big M. And so that tells us that the period t is equal to 2 pi times the inverse of this, which is big M plus 1/3 little m over k. And so that's the period for our system. That's how the mass of the spring affects it.